I'll be talking about logging in distributed compute nodes on robots, where I mean a robot that has multiple devices on it, not necessarily a swarm of robots or the such. And for what I'll be talking about today, I'll be giving you a bit of background on myself and on Blue River, a bit about the middleware stack that we use for context, and then I'll be talking about time and how we deal with logging it, because that's one of the core issues we've encountered when dealing with logging data on these systems. The main relevant thing is that every single project I've worked on in robotics over the past however many years has involved multiple devices on the robot that have to communicate, and you want the code to be following the same structures on every device. That's even true for that high school robotics team. And in fact, that actually has some workable examples of using the same middleware stack that I'll be talking about here that I didn't include a link to here, but if you search 971 GitHub, you can find it. I won't promise anything on the documentation quality, though. Blue River. I work on the See & Spray team at Blue River, and what we provide is a add-on to self-propelled sprayers like the one in that picture that, while driving the sprayer along the field at 15 miles an hour with a 120-foot wide boom, we can get images from 36 cameras and in real time turn on and off nozzles to selectively spray herbicide depending on whether there's a weed in the image. As you might imagine, that has some timing constraints. We need to be able to go fast enough to be productive for the farmers, and we need to actually be able to spray on time. And we can't just sit around crawling around at 1 mile an hour or the such. It's not a safety situation, so if we somehow miss timing once every so often and we accidentally spray slightly incorrectly, it's not the end of the world, but we don't want to spray incorrectly. And it's also the case that these aren't just 10 independent systems. It's not, oh, we can make it so that everything on this sprayer is acting separately and doesn't have to coordinate. It has to coordinate in real time, and when we have an issue in the field, we need to be able to take the logs off of the machine and understand what was happening on the system and how it was being coordinated. And that's why I'm going to be talking about logging here. So about AOS, that underlines for a link that is not terribly useful to you all here. The AOS is the middleware stack we use. It is relatively custom. It is open source. As I mentioned, you can find it with enough effort. We use this for a variety of reasons. This is not an exhaustive list. I was coming up with things to list, and these are reasonable. One is that we care about real-time performance. As I mentioned, we have a system with reasonably strong timing constraints, and a lot of the robotic systems we've dealt with have those timing constraints, and we want to have APIs and a middleware that encourages that. We want to have reasonably low overhead. We've worked on some pretty low capacity platforms over time. That's less true of Blue River's use case right now, but that's something I've seen in other situations. I say single-threaded application code. The important thing there is that what we try to accomplish is having a reasonably opinionated API that makes it so that if developers are going to do something weird or complicated, they know that they're doing it. We don't want to make it so that, it's normal for every single developer to have to coordinate multi-threaded nonsense in their applications. We have static configurations of all our message channels or topics so that if you are going to have a message channel that is going to use a lot of network bandwidth, you have to configure that. You can, but you have to configure that. And then probably the most important thing is the bottom two, which have to do with logging and log replay as well as testing and simulation, where we want all our code to look and behave the same regardless of whether it's in simulation in a test or in running against a log or anything else. And that also means that when we have logs, we want them to capture, to the greatest extent reasonable, the state of the system as it was running. That includes when things happened. That includes when things happened at different times when messages were forwarded across the network. That includes if a given message was dropped across the network. And so if you have something being replayed for one device, it should observe that message drop. Was debating how much to talk about here, but just to give a bit of context on what some of our configuration looks like, since it does become relevant for what we end up logging. on any given channel, or as I said, topic equivalent, and one other terminology note that I may mess up is we chose to call our physical devices, each of those 10 computers, a node. I realize that overlaps with ROS terminology, so I'll try to just say device here, but I may mess up. And any given channel, you'll configure the channel name and type. You'll configure what node it's sent on, and then also what nodes it may or may not be forwarded to, so that we can pre-configure the kernel buffers for the network, so that we don't drop things when we're sending and receiving them. And we're configuring message rates and sizes so that we can configure our shared memory queues so that we aren't dynamically allocating memory needlessly. But yeah, that gets to the actual problem at hand, which is the time is hard. I think most people in here probably know that. Time is hard enough when you have one computer. It's much, much worse when you have multiple computers. But just to talk about what can happen when you have only one computer, you can have real-time clocks, where I mean like a wall clock, not a clock that has real-time performance. And a lot of things, like most people, when you load a MCAP file into Foxglove, by default it'll show you a real-time clock, even if you're using like a system monotonic clock, although there've been some improvements in that over time. And if you're using that as your x-axis in a plot, how do you tell what's happening in these situations? Like, your real-time clock may receive an NTP correction that suddenly slows down your clock for a short bit. And maybe that means that you suddenly see your, what should be a periodic message, have a gap widen up a bit. And when you're just looking at that plot and trying to debug some weird issue on the robot that you don't know why it was happening, is that because you're using a weird clock to display it? Or is that because there is something consuming all the resources on your robot, and so that process slowed down? Or equivalently, if there's a gap in the message signal, is that due to your clock being weird, or is that due to there being actually a gap in what happened on the robot? And so this is to emphasize, you have to care about this if you are trying to debug certain types of weird issues. You can get away with not caring a lot, but yeah. For that reason, actually, we typically generate our MCAPs for visualizing with Foxglove with monotonic clocks based on the time since system boot, since those tend to be more consistent and correspond to the actual timers we use on the system. When you have multiple devices, it gets even worse. The monotonic clocks on multiple devices, the oscillators may oscillate at different speeds, and they may oscillate at different speeds inconsistently over time. We have encountered issues where if the plot on the right isn't too important in terms of exactly what it shows, but that's an example of, okay, we have a bunch of information about the offset between clocks on two devices based on the fact that we can see message traffic going in each direction. That gives us a lower and upper bound on what the offset between the clocks is, but those lower and upper bounds will change. You can generate an estimate, but generating estimates is harder than you would like, and if you want someone to talk about that, you can talk to Austin. But it's challenging, and this can create additional problems when you want to look at the data from your robot. Because if you have clocks that go forward at slightly different times and you have a 100 hertz signal over the course of many minutes, if you go to look at the actual time at which those occurred, order in which those occurred, many minutes later, may be different depending on what clocks you're using to observe that. And right now, if you were to look at most logging formats, like for instance MCAP, there's not much direct provision for including enough information to even record this. And if you look at visualization tools, we honestly don't have great options for that right now ourselves. We just pretend we're looking at something from the perspective of one device. And that sort of fits in with what things like Foxglove support. The other fun one that I think is easy to assume is easier to solve than it really is figuring out what order things booted in. So if all we have is information about messages passing between two devices, and we know on each device what time it was sent on, for some definition of sent, and what time it was received by the other device, what order do we think boots A, B, C, and D, E, F are in? There's very reasonable ways you can get this pattern of message traffic and have both orders. For instance, that arrow that goes from like the started time on node 1 to boot ABC, we could if boots DEF and ABC are in that order, we could very plausibly have had a situation where we had some reliable QoS setting on that message channel. And so when the ABC, whenever node 1 boots up in either boot, it attempts to send it across, but maybe node 1 was misconfigured on boot DEF. Maybe it had too small of a memory buffer and it couldn't receive it. And then that setting got fixed for the next boot for some reason. And so it never got that message, even though it had reliable quality of service settings. And then on the next boot, it did get it. That would explain this pattern of message traffic. You could use almost exactly the same justification for swapping the order of ABC and DEF. And you can log enough information to disambiguate this. It's absolutely possible. It's just not always trivial. And if you want to be able to get logs off of your robots and understand what happened without every single time having to have a human go in and stare at the nitty-gritty of exactly what happened to try to infer what was going on, you need to set up your infrastructure right. And right now, there isn't great infrastructure out there for helping with that I'm aware of, other than what we have. And so what do we actually log to try to accomplish this? I'm not going to try to talk about how we actually then process the data, because that is a bit too complicated. But we are overly verbose about what we log. We have our attitude over time has been that we would rather use a few extra bytes in the log than lose our sanity. And so we get information about our monotonic and real-time clocks on every single message. We log boot UUIDs for what the boot a message was sent from and where it was received. We make sure we're logging the received times on the destination device and when it was sent on the source device. And I think there's some other things in here that I forgot to mention, but basically we're trying to log enough information that we can, to the greatest extent possible, reconstruct what was happening on the system, and then also be reasonably efficient about actually logging it so that we don't have an ultra-complex log writer, and we should have more of the complexity into the log reading, so that if we don't want to have bugs in our log writing code because we don't want to corrupt data. If we have bugs in our log reading code, we can fix those and reprocess data. And so we have erred on the side of logging a bit more data than we probably strictly need. And if anyone ever wants to figure out a minimum set of data that you actually need, be my guest. To talk about a bit about how we use logs, especially in the context of some of the challenges I was mentioning where it's hard to visualize some things well. One thing we do in whatever middleware supports is we can replay any of our application code against a log and have a deterministic replay that, assuming the application code wasn't doing anything it shouldn't, which we try to make it hard to do things you shouldn't, it'll replay the same way it did on the original system. Including, as I was mentioning earlier, if a message was dropped across the network, the message will be dropped across the simulated network. When a message experiences latency crossing the network and the original device, it'll experience latency in the log replay. For something like Foxglove, or honestly most of our visualization tools, with at least one exception, we convert things to effectively being a single node view of the world, because Foxglove and MCAP only really have a concept of one clock. And so we make that avoid the complexity by just saying, okay, we're going to pretend we're only looking at this from the perspective of one device. That is some challenges where if you want to look at what was happening across multiple devices, that's hard. We can do that if we wanted to, but it's not as obvious what is correct. And we have things like this custom panel we wrote in the bottom right for displaying what all the clocks in every single system was. Like we have 10 devices. Well, guess what? We have 10 boot counts. We have 10 monotonic clocks for each system, and we have 10 real-time clocks. The real-time clocks are in pretty good agreement in this log because there wasn't anything funky going on within TP, and so it's doing its job. And everything booted at around the same time, so the monotonic clocks are within a second or so of one another. We have weirder logs out there. Yeah. So in summary, doing this well requires a lot of thought. I don't know that there's great tooling out there in general. The common log formats like MCAP unfortunately don't yet really support this stuff as a first-class citizen unless you really, really trust your real-time clocks being perfectly synchronized across the whole system. And The tooling, we don't have a good answer for visualizing things, and I haven't seen any great options. There's other things like other things I can complain about with log formats. Like right now, we can configure channels to be logged across any number of our devices in any combination, so we aren't saturating the network with just logging traffic unless we want to. And so that means that in order to actually collect our logs into something that can be turned into an MCAP to be looked at with other things, we have to recombine them afterwards. And so that isn't something that's perfectly supported by existing tooling, but I don't know what's out there.